Rams Precision Garage. All right. Hello, 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 Avani. Hello, Avani. Good to see you. Good to see you, Christopher Rams Precision Garage. Or hello, hello, and Yoon's Precision Rodent, or not rodent. Sorry, animal. Hello, Michelle. Hello, Treska. Good to see you all. Okay, here we go. Um, I'm afraid of what's about to happen in this class. Okay. The chat. Good wait, sorry. Good afternoon, Melita. Good afternoon, hi you. Oh, hello, hi you in both ways. Hello. Hello. Good afternoon, Avani. Oh, yes, I said hello. Okay, yes, hello, Avani. Okay. Good afternoon, Marilyn. Good afternoon, Melita. In both ways. Good afternoon, Matthew. Where's Matthew? Yes, good afternoon, Matthew. Good afternoon, Yeyoon. And Cheska, who's saying hello to somebody. Oh, oh, okay. Okay. I was wondering about it. Okay, well, no wonder we're gonna get started quickly before Amanda can throw us off. Okay, just kidding. Okay. Good afternoon, Freddie. All right. I think that's it. Did I say Marilyn, Matthew? And I can't tell. Did I just make fun of somebody? Okay. Wait, and who is with this? Okay. Is that I love that. Is that the eighth floor? I love the eighth floor.
Yeah,
Oh,
we're on the 8th floor.
you're on the okay, and you're together. Right. Okay. I
Yeah, all
almost
three of us.
Oh, okay. Hello. That's awesome. Wait, who's the third? Wait. Oh, you
That's
oh
to say
yeah.
hi.
Okay, great, great. Oh, that's so weird seeing it both in the same. Oh, that's bizarre. Okay, anyway, good, good. No, I like the more the people work together, the better. And the eighth floor is a great, it's a couple. Oh my God. Even that's hilarious. Okay.
Yeah, I'll
Um,
be sorry for being late.
no, that that's fine. Thank you. I will also admit, all right, we'll get going, but I mean we'll get quickly things done before Amanda comes. Just kidding. But before COVID, when I used to work there all the time, like super late at night and blah, blah, blah. And sometimes I had my older son with me, who at the time, okay, I'm just going to quickly say, you haven't met my older son yet, but at the time he was, well, this is before, whatever. He was like 13 or 14 or something. And if I was there really late at night with him, like 1 in the morning or something, we would go up. I can't believe I'm saying this on video, but we would take a break and go up when I was working and he was trying to do homework or he was like watching movies on my computer or something, and we would go up to the eighth floor and fly drone like remote control not drones but like remote control helicopters, and we'd fly them up on the eighth floor like super late at night, and it was probably the most productive work I've ever done. Okay, all right. Yes, an older yes. Okay. Oh, oh, that's too bad. I was wondering. Okay, sorry. That's too bad. If it was fun, yeah, it was great. And totally, inappropriate. Wait. Okay, so we're gonna get started. Good afternoon. Yeah, good to see you. We're gonna get started. Okay, yes, good to see you. Good and good day, Michelle. Oh, wait, I'm looking at another. Hey, is that my Meowscarati? Yes, she took the hint. Oh, that I'm opening a portal for that. I mean, I knew she'd come through. Not only a Pokemon, well, I think. I mean, it's kind of an anime version of it, but that is totally Meowscarada. Am I wrong? I mean, yeah. All right, that is communication. Because that is my favorite Pokemon right now, or certainly that's my favorite Scarlet. And I have a whole deck to. Okay, whatever. I mean, oh, that's great. Okay, sorry, I should not take that too seriously, but I do. Um, I mean, okay, we're gonna start, but that makes me so happy. Okay, it shouldn't. It's totally unprofessional. Wait, what was I just gonna say? I was gonna say something almost substantive. Well, over here, let me switch the board so I can force myself to get into physics here. But oh no, yes, someone did put in the chat. Okay, it's like private chat, so I'm not. But apparently, some people were trying to find me yesterday, and I feel bad because I was totally hanging out, and I was wondering. I thought, in fact, some people even made appointments, and I was there to answer questions. But so let me tell. Yes, I'll quickly tell you again. This is for everybody. I mean, obviously, some people are asking, but because it is hard to find me, and I do like being able to meet people in person, and it doesn't work for everybody's schedule, but if it can work for anybody's, it does. help a lot to meet people in person. So first of all, this is my room again. The best time to find me, I know this is not the part that was confusing, but the best time to find me physically, because it is limited these days, is 11 a.m. to 1 p.m. Tuesdays. It's best if you let me know I'm coming, so I make sure to be there. But how to get there is, on the fourth floor. If you come out of the point is that it's on the fourth floor, but it's right near the jaywalk, like where you guys are sitting right now on the 8th floor, or some of you, like transform that down to the 4th floor. What I mean is don't go into those back hallways where all the offices and labs, where you usually find professors and labs and offices in like the back. That's not where I am. I'm in such an obvious place that it's impossible to find because you would never look there. If you just come out of the elevator on the south side, I think it's the south elevator is like the men's bathroom side. Forgive me, just happens to be the way. If you come out of the elevator and you turn to the right, so you're walking toward the jaywalk, you're like looking at the jaywalk and walking toward it, not going into the back at all. Right before you get to the window of the jaywalk, I'm not saying you literally can go to the jaywalk, but before you get to the window, looking at the jaywalk on the 4th floor, not the 5th floor, the 4th floor, right there to your right is a door that you wouldn't know is there, but once you see it, you'll see my name is on it and all kinds of stupid like Pokemon things and stuff are on it. Like it's obviously my door. It says Science Cognition Lab on it. But anyway, that's where it is. I don't know. And if you would text me privately or email me privately and I'll like break down the directions better or whatever, but it's there right before the jaywalk on the 4th floor. Okay. And the window, anyway, whatever. Okay. All right. So I'm not the imposter. That's hilarious. But yeah, no, please do visit. And it's better if you let me know you're coming. Yeah, please do. Try again. Sure. Especially because we have like this cerebral get together coming up. Okay. I would love to see you. Anybody, whoever, I mean, not just the people. Okay. Anyway. So let's get to physics here. Let's get to physics. What we're going to get to today, apparently some people told me they were happy that they did the big old duck. Yes, some people have been waiting to see the big old duck. I'm glad if it helped people. It's good. I thought Michelle was here. She took her Pokemon and she went home. Okay. Or she went to Route 1. So what we're going to do now is finally get to homework 7. We're going to get to homework 7. Homework 7 really gets into 2 dimensions. I want to say again what 2 dimensions is all about. The whole thing about 2-dimensional stuff is the use of vectors. But the whole purpose of vectors, the whole purpose of vector arrows is to give us a mathematical way of reducing every 2-dimensional problem down, or breaking down every 2-dimensional problem into 2 1-dimensional problems that we solve independently, but then we say they're occurring simultaneously. Okay, so to do 2-dimensional stuff, it doesn't require new physics equations. It just requires a mathematical technique for breaking apart a 2-dimensional situation into 2 1-dimensional situations, each of which just uses our old physics equations. Okay, so the physics of what we're about to do is Galileo's principle of relativity. Good afternoon. Uh-oh, she's here. I mean, hi, Amanda. No, I'm just kidding. No, it's good to see you. I'm totally kidding, but I'm like worried about what's about to happen. Chris has already put his shield up. Okay. So there's no new physics equations once we enter the land of 2 dimensions or 3 dimensions or whatever. What there is, yes. Okay. Oh my God. High punch. Okay. I'm going to just ignore the chat now. Sort of. I'm going to pretend to ignore the chat. There's no new physics equations to move into higher dimensional physics. There's just the math of right triangles. The math that we use to get into 2 dimensions or 3 dimensions, or whatever, is the math of right triangles, right triangles, because our whole thing here is going to be to break break apart every diagonal line into a horizontal line and a vertical line. Again, to say that whatever's happening like this in physics is really something that's happening like this, while all at the same time, but independently, something's happening like this, if that makes sense. So the math that we use is the math of right triangles. And what that really means is SOHCAHTOA and the Pythagorean theorem. Like, that's all that we're sort of adding to our life now, or resurrecting into our life, is Pythagorean theorem and SOHCAHTOA. Those two taken together as one equation is the one that's right here on the board. Like, if ever I say sine squared theta plus cosine squared theta equals 1, you might remember that as a trig identity. You might even remember it as like a random memorized trig identity. But if you like start really thinking about it, if you think of sine of an angle in some right triangle as opposite over a hypotenuse, and you think of cosine as adjacent over hypotenuse, you really start realizing, if you really start thinking about it, you realize that sine squared, you realize that like opposite over hypotenuse squared plus adjacent over hypotenuse squared equals hypotenuse squared. Like, really, that trig identity is just a way of combining Pythagorean theorem with SOHCAHTOA into one equation. So whenever I write that, or if you see that on an equation sheet in an exam or something, that's a shorthand for saying all the math of right triangles applies and we're going to use. And by all the math, I mean SOHCAHTOA and Pythagorean theorem. Okay, so that's a shorthand for those concepts. Okay, I'm going to turn the page. So we're going to now apply this to homework 7. We're going to start, we're going to get straight to it. In homework 7, we're going to go to I'm going to go straight to part B. I mean, part A, if we could understand part B, you could definitely retro understand part A. Part A is just like sort of the warm up in one dimension for it. But our whole goal here is to get into 2 dimensions. So we're going to go to part B of problem 1. I'm scared to look. I'm going to look at the chat in a second, but I'm scared to look. I have a feeling that what's going on in the chat is more fun than physicsy. But I will look in a second just in case there's something serious there. This diagram is a little confusing. Hold on. All right. So in problem 1, part B is all about like the Toyota and the Pontiac and the gas station, and it sort of tells you. It sort of tells you just like step by step how to draw a certain diagram. So I did that. I didn't do it very well. I didn't do it very much to scale. Yeah, okay, so I'm going to talk about this diagram for a second, but so this is the diagram for that problem. G is the label for the gas station, T is the label for the Toyota, and P is the label for the Pontiac. Okay, and I'm going to add a couple of things to this diagram. But I want you to notice, okay, like the diagram sort of asks you to put in an implicit x-axis. And part of the reason for doing that is I want to explicitly label in the x-axis, like I want to decide which direction is positive and which is negative. So I'm deciding that east is positive and west is negative. Again, you can make whatever choice you want, but you have to make a choice and you have to stick to it. But I also want to make clear, even though the question doesn't really tell me to do this, there's also a y-axis going on. And whoa. Oh, sorry. Okay. I also want to make a y-axis, for standing for north and south. And I want to make it clear before I go any further that on the y-axis, the whole point of all of this is like physics is happening while independently yet simultaneously physics is happening, right? The laws of physics are being enacted in each coordinate system. The laws of physics are the same in all coordinate systems, which means ultimately all axes. So therefore, I label plus and minus on one axis, but I also independently label plus and minus on the other axis. So I want to say right from the get-go, like part of the purpose of this diagram that the thing asked me to draw, I mean, there's many purposes of it, but part of the purpose is to start getting straight right away that our, like the whole thing of vectors, vector quantities, is that vector quantities convey magnitude and direction. Up until now, we lived in one dimension of space. We lived on a number line, everything we were doing tonight. So direction could be fully captured by the choice, positive or negative, like whether you're going forward or backward, or north or south, or east or west, or left or right. All of that could be captured by plus or minus, because in one dimension, you only had what physicists call 1 degree of freedom. There was only one choice to be made. So it could be fully captured by the two options, plus or minus. Now that we're in 2 dimensions, plus and minus still applies. We're not getting rid of the power of pluses and minuses, but they apply independently to each axis. So from here on in, if you want to express direction in 2 dimensions, it is not good enough to say negative. Negative only apply, like negative is ambiguous. If someone says, what direction is he going? And I can't say 30 miles negative. Like, I don't know now if that means negative in the y-axis or negative in the x-axis. So altogether now we have to express direction with angles that are accompanied by points of the compass, right? Or at least the way physicists do it is you always express direction with an acute angle, an acute positive angle. So like an angle between 0 and 90 degrees. And then you specify further, like then you, in effect, you give an acute angle and then you specify what quadrant you're in by saying something like northeast or southwest or something like that. I'll be more specific about that in a minute. So what I'm really trying to say here is that from here on in, we still really care about positive and negative, but positive and negative is like a step along the journey. Positives and negatives is what we use to independently track what's happening independently on each axis. But once we put all of our information together and we have a statement about the 2-dimensional plane, then there should never be any negatives in our final answers anymore. Once we're in the 2-dimensional plane, our final answer is always expressed with a magnitude and an angle and points of the compass. Okay, all right, so I'm just saying that. So I have these independent axes labeled. East and west is plus and minus, north and south is plus and minus. Okay, that's number 1. Okay, I'm gonna keep talking, but I'm gonna look in the chat just in case there's something real in it. Oh my God, it's so funny. No, you're right. I can't ignore the chat for a number. 1, because it's irresponsible. 2, because I do love the jokes. Okay, so high punches you, JK. Okay, so good. But yes, it is all about so good. See, notice how Chris, like, he throws in the jokes, but he always throws in something serious too. Oh wow. Okay, that's a good joke. Okay. My life. Yeah, did you say your wife? Your wife is a joke? That's so rude. Oh no, his life. Okay. It's so rude for me to imply that he has it. Oh, don't even get me started. Oh, okay. We all know the game of get the teacher off the topic. Like in some classes, it's a fun game. In this class, it's like not even a game. Like it just happens automatically. But I'm not going to take that bait. You know, if you really want to get me off the topic, which is probably not a good idea, like as an exam is approaching, you know, don't get me started on my sympathy and support for all of you as STEM majors. I know. If I'm not careful, I will go off for a half hour singing my praises unto you, all of you, and giving my like weird motivational pep talks. Like, don't get me. I mean, you know it's going to happen if I'm not careful. I don't think the day's today to do it, but I know your life as STEM majors, all of your lives as STEM majors suck. I know. I think it's worth it. I do think it's worth it. And my hat is off to all of you for doing it. It will, the return on your investment will occur. But oh yeah, I don't want to be you right now for sure. Okay. I just want to give you all a job later. Or at least a recommendation. Okay. So now we're going to get into this. So I've drawn the diagram. Now I want you to note that the diagram I've drawn involves some arrows. Right? Just like the diagrams that you drew in lab 3 involved a lot of arrows. From here on in, we use arrows. So there's a subtle distinction now. We've been talking about vector quantities in physics. A vector quantity is any quantity that, or any measurement that has magnitude and direction. That's a vector quantity. From now on, we use something that we call vectors to represent, to physically or graphically, to pictorially represent vector quantities. We use, so from here on in, a vector is an arrow that's meant to represent a vector quantity. But let me be very clear about this. When I say represent, I don't mean it in a loose sense. I want to say, even when my drawings are bad, we're going to take arrows very seriously from now on in physics. Arrows are used to represent vector quantities. They're not just rough sketches. They're not just they're not just rough sketches. Arrows are used as tools to actually do math, to actually perform computations in the same way that graphs, when taken seriously, represent relations between independent variables and dependent variables. And I know many of us still hate graphs. I understand that. But one of the reasons you hate them is because, you know, if you do, is because, you know, we take them seriously. Like, you have to be serious about them. Like graphs, right? They can be rough sketches, but they're also literal tools. When we say they represent reality, we mean we have a careful one-to-one correspondence going on between the information in reality that we care about and the actual like dots and curves on a page. They're serious representations, and they seriously convey and relate and compute information. Now, same thing with these arrows. They can just look like kind of jokey ideas at first, but an arrow, a vector is an arrow used to represent a vector quantity. So, okay, by the way, I am going to solve this problem. The goal of today is for me to do this problem, which by the end does get thick. I'm not going to do any other problems, but today I will do this problem 2b. And the whole problem is an exercise ultimately in addition of displacement vectors. So we're going to do it, but of course, like all the other time in physics, I'm using the problem as an example to explain a larger concept and teach a larger thing. So bear with me. I'm like going to be making like lots of comments and stuff as we go. Right now, I'm just commenting on the diagram that we made of this problem. This diagram is in fact a vector diagram. And I've tried to draw it sort of to scale. I didn't like literally get out a ruler, and I wasn't exact about it, but I'm trying to draw it, you know, in some kind of accurate-ish way, so that I can follow the following ideas. From here on in, a vector represents. A vector is an arrow that represents a vector quantity. The length of the arrow represents the magnitude of the vector. And I mean represents, like you try to you pick a scaling factor and you try to stick with it. So if one car is meant to be 60 miles away from another car, you maybe draw an arrow that's like roughly 6 centimeters long. And then if another car is 30 miles, then you make that arrow 3 centimeters long. Like, I'm not saying you kill yourself over it, but you are trying to convey information with these arrows. So the length of the arrow represents the magnitude of the vector, and the tip to tail orientation, like where the tip is and where the tail is, represents the direction of the vector quantity. Okay, now all that probably seems sort of obvious, and maybe it is sort of obvious, but bear in the back of your mind that the reason I'm, as usual, going to like drag this out and say a lot about this is these vectors right now in this problem that's about a Pontiac and a Toyota, these vectors right now are displacement vectors. They are arrows that are meant to represent actual distances and directions in space, right? Just like you did in lab 3. So right now, these arrows are literally, they're like maps. They're just like scaled down versions of actual distances that exist in space. Like I just said a second ago, like we might have a 1 centimeter arrow signifying a 1 mile separation in actual space. So hopefully whatever you see in my pictures of arrows sort of pretty directly corresponds to what you might visualize in your mind as the actual situation. What I want you to know in the back of your mind, as I'm giving you these rules about vectors, the power of vectors is that they're somewhat straightforward, I hope, somewhat like reasonable, intuitive to picture when we're using arrows to represent displacements. But every bit of math and every bit of physics that we say about these displacement vectors will also apply to velocity vectors, acceleration vectors, force vectors, field vectors, any quantity at all that has a size and a direction, we're ultimately going to represent with these arrows. So ultimately, these arrows start meaning things that are a lot deeper and harder to picture in our minds than straight up distances. So these rules are meant to allow us to compute things that are harder to picture and harder to draw than just distances. But we start the whole thing in the hopefully most picturable case of displacement vectors. So anyway, how long an arrow is means the magnitude of the vector, and where it's facing represents the direction of the vector. Like I said a minute ago, the way we indicate direction or talk about direction from now on in higher dimensions is we use angle theta and we use points of the compass. Okay. Oops, sorry, do that every time. Okay. Now, note, this is not totally obvious to everybody. Like, this confuses people sometimes. When we say, from here on in, if we say 30 degrees northeast, okay, like, what does that mean? What that really means is 30 degrees north of east. It's just like when we say VAB, like in those velocity things in GPR4, when we say VAB, we mean velocity of A relative to B. We mean velocity of A compared to B. We mean we use B as a basis of comparison, and then we like look to A. Same thing. You may or may not have ever realized in your mind like before, but when we say 30 degrees northeast, what we really mean is picture something that's pointing east. Draw a dotted in your mind. Okay, that's kind of tilted, but in your mind, draw a dotted line that's pointing directly east. That's meant to be hard. So that line was meant to be horizontal like this. Okay. And then raise an arrow. Well, if you say north of east, then bring an arrow. If you say 30 degrees north of east, bring an arrow 30 degrees north of that reference line that you just drew in your mind. That's what northeast means. It means north of east. So, and similarly, like south of east would mean bring the arrow down, below the east, whatever. Which means that technically we can even say things, and we do in physics. We don't so much in like America, but you can say things like 30 degrees east, north. Sometimes you'll see that in textbooks or websites. You could see something like 30 degrees east, north. And if you're following what I'm saying, you'll realize that 30 degrees east, north is not the same direction as 30 degrees northeast. 30 degrees east, north would be like start with a reference line going like that and bring an arrow east of it. So if you're understanding what I'm saying, you'll realize that 30 degrees east, north really means 60 degrees northeast. Okay. Now, but usually we express, I did it again. I tried to erase it and it's still not horizontal. But okay, you understand what I'm saying. Usually we compare to the horizontal, like in English and in physics, we compare to the horizontal. Therefore, one big tip that I'm going to say over and over again, and some of you will catch, since we usually compare, since most of our angles are drawn with reference to the horizontal, like we say northeast, or we say southeast, or we say southwest, or blah, blah, blah. A really good strategy and a really good habit to get into is whenever you're drawing components, whenever you're drawing arrows, and you're about to draw a vertical one and you're going to draw a horizontal one for whatever reason, the best habit to be in is always draw your horizontal first. Whenever you have a choice, you'll see what I mean. But whenever you have a choice, when you're about to draw two different arrows and put them together, in like one's vertical and one's horizontal, because that's the whole point of all of this. When you have a choice, always draw your horizontal first, because generally we measure everything with reference to the horizontal. Okay, that's just like a side tip, but okay. So this is what angles mean. Okay, now I'm going to give you a couple quick rules about these vectors, and then I'll go back and solve the problem, obviously. But like again, like I want you to know this is a strict thing. This is a vector, which is an arrow, is a computational tool. It's a representation, like a graph or like other things. But it's meant to actually like do math for us if we take it seriously. It's not just meant to give us an approximate idea of things. So I'm going to give you a couple of rules of how they work. And these rules will apply no matter how abstract the quantity is. Even if your arrow represents something like electromagnetic field, then the rule, or something that's like really hard to picture, the whole point of the arrow is to take something that's hard to picture and make it easier to picture. And whatever rules I'm about to say will apply to any vector arrows whatsoever. Okay, so first rule, like rule 1A or whatever, is sorry, okay. Oh my God, how are you? Okay, so rule 1A is only the size and the orientation of the arrow convey information. Again, it almost sounds obvious. I mean, it is, like I'm saying, it's an arrow. The length of the arrow represents magnitude. So I should say only the length. The length of the arrow represents magnitude, and the oh, that's weird. Okay, sorry. The length of the arrow represents magnitude, and the orientation represents direction. Okay, like I've said that a million times, that's fine. But now I want to stress something that never occurred to me for years and years and years, how important it was. Only those two aspects of the arrow mean anything. The two aspects of the arrow that mean anything at all are how long it is and which way it's facing. Okay, so that's all of it. So what? Like, why am I making a point of that? Because that means any other aspect of the arrow does not mean anything. And that means any other aspect of the arrow is up to you to choose. Specifically, and this is like a weirdly deep point, where the arrow is on the page, like where you actually put your arrow on your page, even if your page like has graph axes on it and stuff like that, like literally where you put the arrow doesn't mean anything. It doesn't convey, it has nothing. The arrow is a tool unto itself. It's like a sticker. It doesn't matter where it is, it's doing, or it's like a Bitmoji, it's doing its thing wherever it is on the page. Now, who cares? Why would I bother to say that? Because that means you can put the arrow wherever you want on the page. So now this is another extension of this deep, deep Galileo principle. The whole Galileo principle is like some things don't matter. Like what coordinate system you're in doesn't affect the rules of physics. Therefore, you can be in whatever coordinate system you want. Therefore, we always choose our coordinate system very deliberately to get convenience and power. Like the whole strategy of physics, the hard part and the art form is realizing how many choices we can make in physics to set things up and make them possible. So every time we have a choice in physics, it turns out we have no choice but to make that choice. I mean, what I'm saying here is the real power of vectors you're going to see is the way we use vectors as a tool is by specifically choosing where to draw the arrow on the page, because that's the one thing we actually have a choice over. And some places on the page turn out to be more powerful than others. They're all equally correct, but some are more powerful and convenient. Okay, so we have to think about where we put our arrows when we're doing vector computations. That's what it says here. See, therefore we can and must make choices about where to draw the arrows. Oh, I'm sorry, Melita. Yes, please. Yes.
Can you explain what you mean by that? Like, why would one page, like, spot on your page be more important?
Right. No, that's a great question. It's a perfect question because yes, that's what I'm explaining right now. I'm going to give you the concrete example of what I mean. Right, because it's a very weird thing to say. Specifically, what I mean is this. When we play, say you already have one arrow on a page. The first arrow you ever draw, you could draw randomly wherever you want on the page. Like there's no significance usually to like the first arrow you draw, but the second arrow you draw, and we're going to do this concretely in the problem that we're talking about here. The second arrow that you draw, if you put the tail of the second arrow you draw right next to the tip of the first arrow you drew, then what you're literally doing is adding the vector quantities. Like the specific thing I'm saying to everybody is and this is like I'm saying arrows are tools. How do we use these tools? We put them together tip to tail. When you take two vector quantities, and remember, or you take two arrows, remember, each one of them has to be drawn a certain way. Like each arrow is specifically a certain length, and it's like facing a certain way. But if you put them, if you choose to put them together tip to tail, then you are choosing to do addition. You're adding the vector quantities. Conversely, I might add, if you put them tail to tail, or if you put them tip to tip, it turns out you're doing subtraction. So this is what, so I mean, Melita's question is like a very good question. Like, I mean, it doesn't sound like I'm making any sense, but this is what I'm getting at, and I'm going to do it concretely in the problem, believe me. But I'm saying it turns out that when arrows are placed tip to tail, what you're doing is you're accumulating the effects of both the arrows. It's like what you were doing in lab 3, whether you thought about this way or not. Like in lab 3, it said, walk this way like 3 yards, like square root, or like, what was it? Like 3 times square root of 2 yards northeast, right? So you drew an arrow on your graph paper and it went like 3. And it said you could choose to put the arrows down in any order you wanted, right? But you were walking in lab 3, you were like following directions and like trying to walk off the center of an island or something like that. So with displacement, you can visualize, like if you drew an arrow from the center of your graph paper and then you drew another arrow, if you started if you started the tail of a new arrow at the tip of your old arrow, what you're representing is like the total amount that someone would walk if they like walked this way and then they walked that way. If you really think about it, you did this, you could imagine one big arrow that went from the original tail of the first vector all the way to the final tip of the second vector. And this is what I'm saying on the next page, that big vector that would connect the two, its length and its direction, were you to be able to measure it or something, would give you the sum, i.e. the accumulated effect of what the other two arrows had done for you. So what, and again, I'm going to make this concrete, like we're going to literally do this in the problem we're about to solve or in the Pontiac Toyota thing. But what I'm trying to say to everybody, to Melita and everybody, is when you place vector B's tail at the tip of vector A, then whatever vector completes the triangle between the two that you imagine in your mind, like that vector C, is literally the sum of those two vectors. Now, the sum, like it's saying here, C equals A plus vector C equals vector A plus vector B. And similarly, then C minus B equals A, or C minus A equals B. So where the vectors are affects like what's happening to them. And I'm going to pause. Wait, let me just look at the time, make sure. Okay, yeah. Like I'm saying plus and minus. Like, let me be very clear what I'm saying. I mean, again, we're going to see this in the problem, but like example, I'm just writing this lightly because this is just totally like an example. Okay, also quick side note, whenever I put an arrow above a letter from here on in, I mean, I'm referring to the vector quantity. If I put an arrow above a letter, I'm saying like the arrow above A, it's denoting that A is a vector. It has an important magnitude size and it has a direction. But then when I leave the arrow off, like I just wrote up here, example A equals 4, that's not a typo. I'm trying to, when I don't put the arrow on, I'm just talking about the length of the vector, the magnitude. So like the size of that arrow is 4, right? But it also has an angle, a direction that I haven't specified yet. So that's a subtle distinction. But if you see an arrow over a letter, it means the vector quantity. If you don't see an arrow over a letter, it means just the size of that quantity. Now, a quick thing just to finish the answer to Melita, and then I'll go back. When I'm saying that vector A plus vector B equals vector C, I mean the vectors. So let's say the size of vector A is 4 and the size of vector B is 7, right? Like say this represents walking, like I walked 4 miles that way and then I walked 7 miles that way. Well, when I say that A plus B equals C, I don't mean that the length of C is 11. I don't think it is 11. Like, even though the number 4 plus the number 7 is 11, right? The number 4 plus the number 7 is 11. That means if I'm thinking about distances, if I walk a distance of 4 and then I walk a distance of 7, for sure, my overall distance that I walked was 11. Like, that, okay, that's adding up numbers on a number line. But if I'm looking at these, not distances, but these displacements, if I'm taking into account direction, if I walk 4 that way and then I walk 7 that way, to say that this plus this equals this is to say if I walk 4 in that particular direction and then I walk 7 in a particular direction, I end up at this point, that corner point all the way at the bottom of the triangle. It's to say that if you wanted to get from to that same location, if you want to cover the same displacement as I did, if you want your final position minus your initial position in two-dimensional space to be the same as what I just accomplished, you could just go the straight line C all the way from the beginning to the end. And that displacement would equal the total displacement that I just underwent. I don't know if I'm saying that clearly, but in other words, the displacement C, I don't think it's going to be 11. It's going to be some number, smaller than 11. Bigger than 4, bigger than 7, but smaller than 11. And that's what we're ultimately wanting to find out, like in the Pontiac problem, which I'll now go back to. But bottom line, I'm saying when you place two vectors tip to tail, you are adding them together, whatever kind of vectors they mean. And when you place them tail to tail or tip to tip, you're subtracting them. All right. Now, that still might not have like fully answered Melita's question, but I think we'll see it more concretely now if we go into the problem and solve it. And here is Miascarada. I mean, Michelle. Okay. So I'm going back to the, okay. So I'm going back to the problem. Okay. So back to the problem. Yeah. Time. Okay. So back to the problem. Okay. First, it asks a couple of questions. It asks like how it sort of warms you up. It asks how far and in what direction is the Toyota from the Pontiac. And it said originally that the Pontiac is 30 miles at 30 degrees northeast of the Toyota. So what it's trying to make sure that you see, that it wants you to see right away that displacements are relative, or positions are relative, just like velocities are. They follow, they're all relative. It all is compared, all these positions are compared to some reference position. And so it all follows the same logic of GPR form number 4, all three cases. In other words, if it told you that the Pontiac was 30 miles at 30 degrees northeast of the Toyota, then the Toyota must be the exact reverse of that, 30 miles at 30 degrees southwest of the Pontiac. In other words, I am implying that northeast is the negative of southwest. Why? Because north is the negative of south, and independently but simultaneously, west is the negative of east. Okay, I'm probably overkill. I think you get it. But so I'm saying, to answer that question, the Toyota is 30 miles, 30 degrees southwest of the Pontiac. Okay, that's just to answer that. Oh, it's 30 degrees just because the problem, good question, but only because it was given in the problem. In the problem, it says, as one of the givens, that the Pontiac, I believe, unless I miscopied it, I think it says in the problem that the Pontiac is 30 miles from the Toyota and in a direction of 30 degrees northeast. So I'm just like taking the information of the problem and reversing it. Does that make sense?
Yeah, it makes sense because what I thought originally was like I was thinking like parallel lines. So I was thinking that like you would subtract from 180.
Wait, that's really smart. Okay, I'm actually really glad you're asking. No, that's really smart. I totally get that. Honestly, I remember I used to do that too. Honestly. Right. So that's why So what I'm saying is, like, that makes sense. I hear you. I'm visualizing what you're saying. But to do that, if you subtract from 180, whether you realize it or not, what you're really doing is you're flipping one of the axes, but you're not flipping the other. You're in a way putting a negative sign on the X, but you're not putting a negative sign on the Y. So if we really want to take negative signs seriously, if I really want to say that my perspective is the opposite of yours, it means I flip the north to south and I flip the east to west. And if you draw that out, maybe I should draw it out. Well, yeah, I guess I'm saying this. Hold on a second. No, that's really good. It's a good, wait, how do I add a page? Hold on a second. I gotta add a page. How do I add a page? How do I add a page? I don't know how to add a page. I don't know how to, okay, sorry, sir. Forget it. How do I add a page? Well, all right. I'll just do it right here. What I think Chris's question, it gets at like a lot of issues. And basically, if one of the vectors was 30 degrees northeast, then the reverse of that, literally the reverse, would be the exact opposite, the mirror image. And if you think about it, the mirror image would be 30 degrees south of west. I'm just, if that, but yeah, it's a great question. Okay, I'll go on. All right. So yes, it's always the same. So again, it's just like GPR form for case 2, where we keep all the numbers the same, but we fully flip the direction. But okay, I think he gets it, but it's a great question. Okay, so now that's that question. Then same thing, it asks, okay, what about the gas station to the Toyota? Well, it told us that the Toyota was 60 miles and 20 degrees southeast of the gas station. Therefore, I just flip it, same thing as the Chris question. Therefore, the gas station is, again, 60 miles and again, 20 degrees, but northwest from the Toyota. Okay, that's kind of warm up. Now, that's kind of like case 2 of GPR2. It's like VAB equals negative VBA, only instead of V's right now, we're looking at displacements. But we're seeing it's the same concept applies. And it's like easier to picture with displacements in a way. So now we're going to go to case 3. In a way, we have 3 objects now. I mean, we do have 3 objects now. We have a Pontiac, a Toyota, and a gas station. So we've got an arrow in that original diagram that I drew. We have an arrow that's pointing from the gas station to the Toyota, right? And then we have this arrow, this displacement that's pointing from the Toyota to the Pontiac. The problem now, and this is the thick problem, this is the part that takes work. This will take the next 27 minutes of the class to do. But once you do this once, it's always the same way. The problem is asking, okay, if we know what the displacement is from gas station to Toyota, and we know what the displacement is from Toyota to Pontiac, like what is the displacement from gas station to Pontiac? So it's really saying, it's 2 things. One, it's just like saying, we want to know, like, in effect, like VGP. And what we're saying is it's not really V, it's not really velocity, it's a displacement, but I'm using that concept. So we want to know dGP, and what we're really thinking is dGP equals dGT plus dTP. Maybe for some of you, I'm making it more complicated than I need to, but I'm just saying this right here, what we're about to do is practice in that whole GPR form 4 case 3 thing that people are legitimately still nervous about. Okay, and I see something's happening in the chat. I'm going to look in the chat in 1 second. But really what this problem is asking us to do is to add 2 displacement vectors together to get a third. What we're looking for is to get the length and the direction of that red arrow that I've drawn in here. That's like vector C, like that's the answer that I'm looking for. And I will look in the chat, but I want to, well, I guess I am, okay, I'll look in the chat. But so we're learning how to add 2 displacement vectors together in order to get a third. And it's not a joke. I mean, the reason I'm sounding so intense is like, we're going to do it and we're going to finish it by the end of this period. And I'm not saying it's hard. but it definitely is like I will put it this way. There's no way, I've done this a million times in my life, like a million. It's not like I could look at that picture and know the answer in my head. No way. Like it is definitely something I have to work through to get the answer. So it is an involved procedure, which I'm about to show you, but there is something happening in the chat. Oh, sorry. It's an involved procedure, which I'm about to show you. But what I'm going to show you is with these displacement vectors. But please bear in mind again, that once you get it right once you see how to do it for 2 displacement vectors, that procedure carries for the rest of your life to any 2 vectors ever that you'd want to add. And if you have to add 3 vectors, you just do the procedure over and over again, etc. So we're like, what we're really doing here is learning how to add. It's like as important as 2nd grade. We're like learning how to add, but we're learning how to add in 2 dimensions, which is a thing. Okay, wait, so sorry, chat. Wait, wouldn't you add both vectors? Well, so the answer is yes. So I'm looking at Chris's question, which is obviously not a joke. It's a serious question. Sorry, I left it hanging. But my answer is yes, you would add both vectors, but I'm not sure if that question is, if you're asking about like where I'm up to now, yes, we're going to add those 2 vectors. But if you're asking about it, about the 30-degree thing, then I'm not sure I understand the question. No, so you're good? We're good? Okay. Wait, we're good, I think. Okay, cool. So yeah, cool, good participation. I love this class. I'm gonna miss this class after it kills me. Okay, so we're gonna add these vectors. That's what we're gonna do. And I'll also warn you right now, it's a procedure. We're going to do it. It's always the same procedure. Certainly it's going to involve trigonometry or geometry, but I also want to warn you and so yeah, you like got to do stuff with triangles, and many of you tried different things. I want to warn you right now, that triangle that I'm looking at on my page, like it has a 20-degree angle in it, it's got some fuck angles. That triangle between the 3 vectors, that is not a right triangle, or I don't believe it is, and there's no reason to assume that it is. Okay, that triangle is not a right triangle. But I want to tell you right now that if you start doing things like law of cosines or law of sines, or if you start getting into issues with that triangle and trying to like do math on it, you're not doing it the right way. I mean, many people do that at first, and you might occasionally by coincidence get the right answer, but you will, our goal, what we're about to do now is we're going to break everything up. Our whole thing is to take this physics idea to say anything that looks like it's happening in 2 dimensions is really 2 things each happening in 1 dimension at a time. So we're going to break this all up into 2 separate dimensions, which means everything we're going to do always with vectors in physics, everything will involve only right triangles. I mean, that picture is not a right triangle, but every math that we're doing should only involve knowledge of right triangles. If you ever start trying to do math on some kind of triangle that you think isn't right, so you start pulling out exotic other math, then something's wrong. You should never have to use the law of cosines is basically what I'm saying. So here we go. I have to get back to the page. Okay. So here we are. Okay. So we're going to add these vectors together. Like Chris said, we're going to add them together. Vectors are such serious computational tools. Oh, wait. We have next semester. Wait, we have next semester. I forgot. We have next semester. I don't even remember what that. Okay. But all right. I know that's funny, but I don't get it. But okay. Oh, yes, good point. Right. Good point. No, I can't wait to see you guys next semester. That's we're really gonna have fun. Yes. Take the in-person version of this class next semester. Take the in-person version. Okay, just saying. All right. Vectors are such serious real computational tools that the whole premise here is that if I had drawn, it all goes back to lab 3 in a way. If I had drawn my 2 black arrows. Okay, right. I hear you. I'm ignoring that, but yes, cool. If I had drawn the 2 black arrows to scale, like with a ruler and a protractor, then I could just do this by measurement. I mean, that's what it's saying here on the board. I would just put a ruler to that red arrow, and I'd put a protractor to it, and whatever measurements the red arrow had, that would be the answer I'm looking for. Like, that's how well vectors actually work. Like, vectors can do the math for us just by drawing. If you draw carefully enough, then you don't have to do any math. They do the math for you. And that's great, especially for those of us who do draw carefully or like using rules and protractors. And again, that's kind of what was happening in lab 3. But once things get complicated enough and there's enough vectors and stuff, most of us don't, we want at least another method as an option because we don't want to be sitting and drawing everything painstakingly. So we have an analytical way of finding the answer. That is what I'm looking for. I'm looking to solve this problem. I'm looking to add 2 displacement vectors together to get a third. I'm realizing in my mind that what I'm looking for are the measurements of that red arrow. Like in the end of the day, that I should get some, I mean, that red arrow is a pretty good indication or approximation of what I'm looking for. Like my answer at the end of the day should be like as long as that red arrow looks compared to the other 2. And if that arrow is sort of pointing sort of southeast-ish or whatever, then my answer at the end of the day better have like a southeast type of angle, right? I'm trying to now analytically get the measurements for what is depicted in that red arrow. So that's what I'm doing. So what I'm going to do is what's called, I mean, there's different ways, but what we do in this class, and what I do only always in my life, is what's called the component method of addition. The component method is a method by which every 2-dimensional vector we see, every diagonal arrow we see, before we do anything else, we break it up into 2 1-dimensional arrows. Like every diagonal arrow, we break up into a horizontal piece, or what we call a component, and a vertical piece, or what we call a component, and we deal with the pieces separately. We're going to mathematically break up a 2-dimensional situation into 2 1-dimensional situations, and we do so with trig. And that's what we're going to do on this page. And while you look at this page, I'm going to look at the chat. I'm scared. Oh, yeah, no. Okay, by the way, I will say, I'm not going to get, no, I always, 204, which I mean, this is also that we can become friends and then we cement our friendship in physics 204. I mean, I love this class, but I love 204 even more. And yes, I always do teach one section of 204 in person and I live for it. It's like my favorite part of the day. However, I don't want to get it, and I want to see you all there. And usually anybody who can take it, I think usually has a better experience. But I'm going to say this right now, and then we're going to move on. Don't kill me for this. The price that if you take the 204 in person, you almost automatically do well, because if you do it at all, you have to do it amazingly, because the 204 in person is always 8 in the morning. I know. There's a reason for that, but it's true. So it's true anyway. But if you can handle 8 in the morning, you win. Yes, way. I'm sorry. All right, we'll talk about it another time. I'm sorry, but oh my God, that was fat. Oh my God. But here's the deal. All right, no, here's the thing though. I swear, the thing about it, I know 8 a.m. is torturous, but the thing about it is that's the hardest part of the class. Anybody who literally can survive that, anybody who somehow can get there for 8 a.m. has done the heavy lift by showing up. And then from then on in, it's a cakewalk. Like if you could somehow get, I mean, okay, we'll talk about this another time, but anyway, are you kidding? I'm not even going to be modest about it. I'm like outrageous at 8 in the morning. I'm like me plus caffeine. No, I mean, because for me too, it's impossible for me to get up. But once I get up, I'm up. Oh yeah, no. Believe me, I deliver at 8 in the morning. Okay, anyway, but now I know you think you're gonna. Okay, anyway, I promise you, my commute is longer than yours. But okay, anyway, and always the people that are coming from the farthest always get there the earliest. Anyway, we're doing physics now. I do sometimes get donuts. That's interesting. Okay, we'll talk. Stop. Okay, so what we have here, what I'm doing here, and some of you would have thought of this, and some people don't think of this, but this is what we always do. I'm zooming in on each vector individually. I'm taking that first vector. I'm calling it T. I'm calling that first vector T. In other words, the vector to the Toyota. Okay, so I'm calling it T for Toyota, right? And I'm zooming in on it. Okay, I'm totally going to ignore the chat as long as I can. I'm zooming in on it. So T was like 60 miles long, right? And it went to the southeast by 20 degrees. So So remember we said before, like Melita and others, we were saying that when you place vectors tip to tail, you add them, right? Well, just like 3 plus 2, just like 5 plus 7 is 12, right? But 5 itself is 2 plus 3, right? Like, okay, the point is this vector, it even before I add it to the other one, I can think of it as a sum of two individual parts. If I walk 60 miles at 20 degrees to the, and everybody who lives in Manhattan, or I mean, who goes to school in Manhattan knows this. If you want to go southeast in Manhattan, you have to go downtown and over, right? We don't walk in diagonals in Manhattan, but we can get anywhere we want. We can get 60 blocks, 20 degrees to the southeast, as long as we walk a certain amount of blocks downtown and a certain amount of avenues over, right? And a certain, right? So what I'm saying here is to go 60 miles at 20 degrees southeast is equivalent to, it is the vector sum of some amount east that we went plus some amount south. Plus means the accumulation. I don't care if we maybe then I don't care if we did it in time or not. There's some way that to add up an amount east with an amount south to get 60 miles southeast. And we want to figure out what that is because, right? So I'm saying for all time, southeast really means some amount east plus some amount south, always. And notice, quick subtlety, notice I'm saying southeast is really some amount east plus some amount south. I could say it the other way, but I'm intentionally saying it that way. I always think horizontal first because everything gets compared to the horizontal. So notice how I drew this triangle. There's other ways I could have drawn it, but they wouldn't be right. Well, I said going southeast. So this is not just, in other words, just a math triangle. This is a physics triangle. It's not just made up of sides. It's made up of arrows. The arrows are key. When this appears on an exam, I'm going to tell you right now that one of the way people lose points when they make triangles and diagrams on vector problems in exams is people who leave off the tips and tails and just start doing raw geometry. Bad idea. This is physics. We are saying to go southeast is to go some amount east and then to go some amount south. And I would advise that you always draw the horizontal first. So, tip to tail, the tail of the horizontal then started, the tip of the horizontal then started the tail of the vertical. Together they make the 60. So the question is, what are those two legs? I want to know. I want to know how far east equivalently did I go and how far south did I? So what do I do? Well, that's definitely a right triangle on purpose. I'm saying we're going to do any vector problem, any addition, before you add vectors together, you zoom in on each one individually and you turn each individual vector always into the hypotenuse of its own right triangle. Note this triangle is just an expansion of one of our vectors. I'm going to say it again. It's saying that two-dimensional direction that we went is really the sum of two one-dimensional directions. And our job now is to find out what each of those components was. And we do this by using right triangle properties, specifically SOHCAHTOA. In math, you use SOHCAHTOA usually to get the angle if you know the sides. What we tend to do in physics, at least in this part of the methodologies, we go the other way. We're going to use the angle to get the sides. So like SOHCAHTOA says, like the cosine of that angle equals the adjacent over the hypotenuse. The adjacent is the horizontal piece, how far I went to the east. So I can multiply both sides by hypotenuse. So I'm saying what I want is the sides. I'm looking for the length of the adjacent and the length of their opposite. They are meaningful quantities. So I multiply both sides by hypotenuse. So I say adjacent equals hypotenuse times cosine of the angle. And that adjacent is the horizontal component of this vector. If the vector was known as t, this is what I just found is t sub x. It's approximately 56.4 miles. that means that when I went 60 at 20 degrees southeast, what I equivalently might have as well have gone over 56.4 miles, right? And then I figured out the same thing for the y. Notice I did it faster now. For the y, I noticed the pattern of what I'm doing, and for the y, I said, oh, it's hypotenuse times sine of the angle. And that's what I'm going to do forever from now on. I'm not going to redo SOHCAHTOA from the base every single time. I'm just always going to say the adjacent side is hypotenuse times cosine, and the opposite side is always just going to be hypotenuse times sine. Sine and cosine are always decimals or fractions, right? They're always numbers lower than 1 or greater than -1. So cosine and sine are just like percentages. They're just like telling you how far over or how far up or down some diagonal line brought you. And so they always return values that are some fraction of that diagonal line. In other words, the legs of a right triangle are always shorter than the hypotenuse. Okay, so the two legs of this triangle I just got, and I needed to get the two legs. I'm just looking at the time. Okay, and I'm ignoring the chat. Sorry, I will look, but we've got 9 minutes. I want to finish this problem. So I just got the legs of this triangle. I need them. It's not just I'm not done with the whole problem, but I need that information. I put it in my mind or I put it on the piece of paper. I bank that information for a minute. I don't do anything with it yet. What I do is I go on to the other vector now. I look at the Pontiac vector. Okay, so there's at the top is a summary of what I just did. And now we go to the other vector. We zoom in on the other vector, the Pontiac. So it was 30 miles at 30 degrees northeast. I quickly do the exact same thing. I say if you go 30 degrees, 30 miles northeast, then you're really going some amount east and you're going some amount north. How much are you going east? You're going 30 times the cosine of 30. I'm just cutting straight to it. So I get 26.0 approximately for the horizontal, for the adjacent leg, the horizontal. And then the vertical leg, the opposite, is going to be hypotenuse times sine of the angle. So, and I will scroll back if you want in a minute. And also, obviously, I'm going to upload this PDF. I know I'm going a little fast right now, but I mean, tell me if you want me to scroll back, I will. But I just did the same thing to the other triangle. So I'm individually, I always do this. I don't care what if I'm adding vectors of any kind, I take each vector, I individually zoom in on it, and I get its components. And the reason is, it's really what you all did in lab 3, whether you consciously were thinking about it this way or not. Because in my mind, what I really understand, what you understood in lab 3 is like X displacements can add together directly, and Y components can add together directly, but not the other way around. In other words, like you saw in lab 3, if you had a bunch of directions and you broke them up and you saw that one crazy diagonal line took you 3 yards east, and you saw that some other diagonal line took you 3 yards west, you knew to like that those two would cancel out and you wouldn't go anywhere on the east and west line. Even while you were maybe doing something on the north-south line, east affects west and west affects east and north affects south. And so what I'm saying is we broke these apart so that we can now independently do physics on each axis. What I always do is I make an XY chart. I like divide the world into 2 coordinate systems, like the horizontal world and the vertical world. And what I say, okay, I'm just looking at the time. I'm going to look in the chat just in case there's a serious. Okay. Okay. All right. So I made a chart and I just took those components and put them in the chart, right? Like the Toyota took me 56.4 miles in the X direction, and it took me 20.5 miles in the Y direction. But if I look, and I'm just watching the time, so but now notice the arrows really matter. This is all about tracking magnitude and direction. If I look at my triangle, like that Toyota triangle, notice it took me 56.4 miles to the east, and we're calling east positive, but then it took me 20.5 miles to the south, not to the north, but to the south, and we're calling south negative, and that matters. So I put a negative sign on that 20.5 in the chart, okay? But then the other one, the Pontiac, took me 26.0 to the east, and it took me 15 to the north. So the other one doesn't get any negative signs, but like you watch the negative signs. So, and notice we care about negatives, but we only care about the negatives like once we're in the individual axes. All right. So now those numbers get added up, because we're adding vectors. We want to know the total displacement. So we're basically saying first you went some amount east. And then you went another amount east. That gives us a total amount that you were traveling east if you went from the gas station all the way to the Pontiac, right? And simultaneously, but independently, you went somewhat south and then you went somewhat north. So I independently add up those numbers. I add them. One of them happens to be a negative number. But so, okay, so 56.4 plus 26 equals 82.4 positive, and negative 20 plus 15 equals negative 5.5. So what this is saying, we're almost done. We have 4 minutes, 5 minutes. We're not done yet, but we're almost done. What this chart is telling me, notice again, this chart is the moment when I didn't invent any new physics. I'm just adding, but I'm adding up X numbers, X distances, independently, and I'm adding up Y numbers independently, but I'm saying they all happened at the same time. I do the physics independently, but then, so in the end of the day, what this is telling me is at the end of the day, if I want to travel from the gas station to the Pontiac, I have to overall go 82.4 miles to the east, and also I have to go 5.5 miles to the south. So to put all this information together into one final answer, into one final red arrow vector, I do what you might think. I make one final right triangle. I say, and you notice I do tip to tail again. I draw the horizontal first. I say, in effect, I went 82.4 miles to the east. And then, like anybody who would walk all the way to the east and then walk south 5.5 miles will end up at the same location as that red arrow would bring me. So in order to get so that red arrow right there, TP, like the sum of the two, that red arrow is the same red arrow that I have on my first page of this whole PDF. If you know what I'm saying? Like that is a blow up of the red arrow that we're looking for in our original diagram. And it's a blow up, like it's much steeper than really it should be. I'm like zooming in on it. But if I did everything perfectly accurately, that red arrow would be exactly as long as the original red arrow, and it would be at exactly the same angle. I mean, of course, it's a sketch, so that's why I have to do all this math to get the exact numbers. So how do I get the numbers? We have 3 minutes left. I do the Pythagorean theorem. I say the length of that final arrow is the Pythagorean sum, the square root of the squares of the two legs, 82 and 5.5. So the length of that whole arrow is approximately 82.6 miles. Notice it's a little bit longer than 82.4, a little bit longer because the south, the vertical leg is much, much shorter than the horizontal leg. In fact, even my diagram is my diagram is like way too chunky. But that vertical, or notice, put another way, we're saying vector-wise, 82.4 plus 5.5 gives you 82.6 vector-wise. If we were adding the distances, of course, 82 plus 5, gives you like 87. If you literally walked out the full distances, you get a number like 87. But that's not what we're asking. We're asking the total displacement. We're asking how far away is the Pontiac from the original gas station? How far away is it as the crow flies, in a straight line path? So if you take into account the subtlety of these directions, then we get that 82.4 this way plus 5.5 that way gives like approximately 82.6 that way. And then we're still not done. We're just about done. We need, if we're getting a vector as our final answer, we have to get a direction as well, which means an angle. How can I get the angle? I think the fastest, most direct way is SOHCAHTOA is tangent. The tangent of the opposite over the, the tangent of the angle equals the opposite over the adjacent, 5.5 over 82.4. So, but I don't want the tangent of the angle. I want the angle itself. So the angle is the inverse tangent or the arc tangent, right? Or tangent to the -1 on my calculator. I've got to do tangent backwards to get the angle. And if I do, and this is always the way it works, like it's the procedure every time, the angle will be the arc tangent of 5.5 over 82.4. And what I get is like a very, very small angle of 3.82. And, oh, and this got blown up. It's 3.82. And I know, and then I look at my picture and I look at the arrows and I looked at it's 4:20 o'clock. And so by taking my arrows seriously and all the negatives and positives, I know that that angle at the end of the day is 3.82 degrees southeast, like south of east. And that's my answer, 82.6 miles at 3.82 degrees southeast. There's no way I could have just seen that in my head, but that's the procedure for getting it. And that's class. Thank you for being said. Yes, come at 8 in the morning next week. I'll have donuts and coffee. But no, I'll see you Monday at the normal time. Assuming I post a practice exam tomorrow, like it would be highly advisable for you to like take a very good look at it this weekend, and come Monday to class with questions, specific questions of it. Well, yeah, coffee, sure, why not? Or Celsius. Come Monday with questions. The more specific your questions are about the practice exam, the more of them I can answer. If you just come in and say, can you solve problem 2? Like I'll spend an hour and 15 minutes just doing one problem and it won't benefit you all. So come with super specific questions and I can answer a lot of them. Have a nice weekend. Thank you. Have a good day. And I'm here for any questions if you, okay. Thank you guys. Good job. God, okay. The chaos. Oh my God, how many? Oh, that's so funny. Now you're like all over that. Oh, that's cray. That is cray. See how much fun this could be at 8 in the morning in 3 dimensions. Hayu's going to do it. Hayu's going to take the class. I know it. No, she's not. Oh my God.
Thank you. Have a good day.
Thank you. Have a good day. That's so mean. I mean, if I'm waking up.
Professor.
Yes. Oh, I'm talking. I'm stopping the recording. Hold on.